Hello everyone. In this study, we propose an energy-efficient long short-term approach for sustainable sailboat autonomy in disturbed marine environment. Sailboats, driven by wind energy, are highly suitable for long-term voyaging, including applications such as ocean observation and ocean mapping. However, constraints in the energy of the onboard controllers, sensors, communication modules, and actuators are crucial for their sustainable autonomy. Reducing control frequency on actuators is a significant method for energy conservation. Therefore, we aim to propose an efficient energy management scheme tailored for real-world marine environments. Firstly, we construct the model for our sailing robot, considering the motions of surge, sway, roll, and yaw. Since sailboats are solely wind-driven, the pulse of sail is crucial for categorizing sailing motion, especially in the no-go zone. The robot is unable to sail due to a lack of propulsion. Two primary tilting maneuvers can be observed: tacking and jabbing. Based on the mentioned pulse of sail, start and go, the robotic sailboat engaged in continuous reciprocated sailing across a given sea region. This figure shows three typical long-term sailing scenarios: beam-ridge sailing, leeward sailing, and windward sailing. According to the wind conditions, the possible sailing motions are generated as shown in the blue straight line or zigzag segments. In the real marine environment, the motion of the robot is influenced by wind, waves, and currents. Consequently, we predict a range of course angles. This angle range serves as a reference for motion adjustments during straight-line sailing. In scenario 1, the sailing path remains within the predicted range. In 2, and the angle exceeds our predicted range, adjustments are made to let the robot back. In our reciprocated voyage, curve sailing also occurs. In scenario 3, a turn is executed, whereas in scenario 4, external interference causes a straight-line sailing to deviate into a curved one. We introduce our proposed EeLsT method, which comprises two components: the long-term observer and the short-term observer, depicted in blue and green boxes respectively. The long-term observer consists of three primary components: data collection, data processing, and estimator training. The estimator predicts the course range for low-frequency motion adjustments. The short-term observer monitors curve segments requiring frequent control. To implement and assess the performance of the observers, we developed two modules: motion analysis and energy analysis. Then, we validate our method through simulation in three scenarios: S1 without wave disturbance, S2 with model-based wave disturbance, and S3 with waves from real experiments. Notably, the sailing performance in scenario 3 closely resembles the real sea environment and is utilized to generate the dataset. The dataset, featuring diverse conditions, is illustrated and employed to train the estimator. Predicted outcomes are graphically represented in terms of wind, tidal currents, and rudder angles. The results fall within a 95% prediction interval, with a mean absolute error MAE of 4.24 degrees. Subsequently, we perform motion analysis and energy analysis across four groups to evaluate the performance of the EeLST scheme against the PID-based baseline method. In scenario 3, the EeLST scheme demonstrates superior performance exhibiting lower average power consumption. In simulation, long-term experiments are also carried out to delve deeper into the proposed method. The results demonstrate that the proposed method is more energy efficient compared to the baseline method. The average working power stands at 27.72 watts, which is lower than that of the baseline method. Next, we provide details of our experimental validation, which involves a catamaran sailing robot named Huihuan. The testing site is located in an open bay with consistent monsoon winds. The main disturbances in the area arise from oscillations and drifts induced by waves and currents. Here is a configuration of Huihuan and the onboard energy diagram. The power distribution is highlighted in red. For sail control, sailing safety and energy efficiency are two crucial aspects. We propose to passively change the sail angle according to the tackle angle. Specifically, the maximum sail angles 10 degree, 25 degree, and 35 degree are considered in different wind default 0 to 1, 2 to 5, and 6 respectively. Such correspondences are based on experience gained from extensive real-world experiments. We have constructed the experimental dataset and visualized the predicted results. The validation results fall within a 95% prediction interval with a MAE of 5.98 degrees. Subsequently, two groups of straight-line sailing experiments are carried out. It is evident that EeLST scheme consumes less average power and conserves energy. The average power in EeLST scheme is 24.84 watts. Moreover, long-term sailing experiments are conducted to further validate the performance of EeLST scheme. The average power consumption is 26.18 watts and 25.19 watts, respectively. Here is an illustration of continuous sailing over 24 hours. Displayed here are the experiments conducted over 30 days with complex marine environments. Each subfigure represents the path recorded for a single day. Altogether, the sailing distance covers 1,200 kilometers and is stored in a large dataset. Overall, the proposed method attains an average power of 25.82 watts, compared to the standby power of 25 watts. The average power realizes only a 4% increase. Here shows the snapshots from videos of different perspectives under varying marine and weather conditions. Additionally, in the diagrams of the two turns, enlarged images provide clear visualization of the turning process. That's all. Thanks for your watching.